So this course is quantum mechanics, and we have block 1, introduction to quantum mechanics, that includes your wave particle duality, uncertainty principle and its consequences, Schrodinger equation, observables and operators. So you can see the Debye hypothesis, and there is the famous equation lambda is equal to h by p. Lambda is Debye wavelength, h is Planck's constant, and p is momentum. So the wavelength of the wave associated with a particle of matter in motion is inversely proportional to the particle momentum, and constant of the proportionality is just the Planck's constant, and it is very much dominant for microscopic particles like electron, protons, photons, so on and so forth. And Louis Debye is awarded with Nobel Prize in the year 1929 for his research, which guided the scientist for decades. And you have also frequency of the wave associated with the matter wave, which can be written as E by H. So before the arrival of quantum mechanics, the classical mechanics started with Sir Isaac Newton and his famous corpuscular theory. So corpuscle or point particles are being considered by Newton for his explanation of light. Then Huygens and other people used wave concept and consider the light as a wave to explain diffraction, interference, and many scientific experiments. And in 1926, Austrian physicist Schrodinger published 4 papers in which the wave nature of particle was treated explicitly with wave equation, and the physical interpretation of that wave equation was given by Max Born, which will be discussed in our later classes. And you can see many experimental findings which are unable to explain by the scientist using classical mechanics. Let us focus on some of them. One is your black body radiation. You can see that there are 2 parts. There is an increasing trend and there is a decreasing trend, and 2 equations are usually being used. One Wien's displacement law, one Wien's law, and another your Carle-Jean's law, which will explain different part of a black body radiation. And Planck's law, in Planck's law, the quantum concept is well used to explain the whole spectrum of a black body radiation. So this is one of the example where the quantum concept was being used. Similarly, your specific heat that was also used being explained by your quantum mechanics. Your Davison-Germer experiment that confirms the existence of matter wave and measurement of electron wavelength is in the formula H is equal to me by V, where H is Planck's constant, m is mass of the electron, and V is velocity of the electron. And electron wavelength can be calculated using the formula H is equal to root over of 2 me in electron volt unit. So then your wave particle duality by your Debye and concept of matter wave, then the phase velocity, group velocity, so on and so forth. So your specificity heat of solids, your black body radiation, and some similar experiments. Your similar experiments cannot be explained by classical mechanics, which was well explained by quantum mechanics. So, what is quantum mechanics and why it is being used for microscopic particles? Am I audible?
Yes, sir.
So, as I told you earlier, you can see in the screen in classical physics the description of particles through Newtonian mechanics, or that of wave using wave equations are accomplished through differential equations d by dx or d by dr or d by dt. A new formalism should incorporate the features of wave particle duality, which I was which was discovered by your the mathematical expression was well established by Debye, uncertainty principle by Heisenberg, and other concepts. At the same time, it should reduce to classical formulation under appropriate limit. Schrodinger's wave mechanics and Heisenberg's matrix mechanics were major steps towards this. So in Schrodinger formulation, a differential equation describes the system under consideration. This is known as Schrodinger's equation and is regarded as the starting point of quantum description of a physical system. Similarly, another is the uncertainty principle, which is an important concept put forth by Heisenberg. So, what is in classical mechanics? You can see, you can with definite precision and accuracy, you can have a value for momentum, for force imposed upon a body or by a body, the uh, work done, uh, the energy of a particle, the potential or field at a point, all can be accurately measured, and you can have a definite value for your force in Newton or dyne. You can have exact calculation of work done or energy in org or joule. You can have a velocity. You can say 5 meter per second or 500 kilometer per second, exact value. So there is a certainty. You can measure the observable quantities in classical mechanics in the day-to-day description of the system around us. But in particle physics or microscopic particles, you cannot measure certain things accurately. For example, suppose there is a particle, suppose there is a electron. Suppose there is an electron in an atom. Let us picturize this. Let us have suppose there is an electron. Okay, so electron is moving. Electron is moving. Electron cannot be static. Suppose I have given you a task. Measure the position and moment of the electron. So when you want to measure the position of the electron, what we will do? Anybody else? How can you measure the position of the mobile or desktop you have with respect to a frame of reference where you are situated at the center of that coordinate system? You just use a measuring tape or scale, and by that you will measure the distance from your body to that mobile or that desktop, and you will say it is 5 centimeter away from the origin. So if it is in Cartesian coordinate system, if you can place it in the x axis, you can say it is at 5 I cap distance from the origin, or its position is 5 I cap. If it is, you can place it in xy plane also. You can resolve the components as x I cap plus y j cap. How can you measure it? By using just a scale or a measuring tape. But if you measure the position of an electron, suppose electron E, which is there in a electrical circuit, which is giving electrical signal to your mobile or your desktop. So how can you measure the position of that electron? Anybody? Am I audible?
Yes, sir.
So what we will do? So you have to incident a photon upon it, and that photon will strike the electron and return back, and from the path traversed by the photon, you can measure the displacement of that electron from or the distance of that electron, or in a vector form from the source from where the photon is being ejected. So what happens? If you incident a photon which is in visible spectrum, visible red to your violet, yes, in between this spectrum, the visible light is there, and you incident that light, and um, uh, you detect the reflected light, and from that uh, distance traveled by light, and from trigonometry, you can calculate the exact position of the electron which you have measured using that light. So what happened? Suppose the momentum of the photon is v. So momentum is associated with the motion of the particle. If the body is having some energy, then it will have a definite velocity, acceleration, or a motion. So when that electron is interacted by that photon, what happens? When a photon is incident upon the electron may absorb whole of the energy of the photon or a part of it. When it absorbs the whole of the energy of the photon, then it will not reflect back. And even then, you can also measure the position of that electron from the light traversed. कितने समय के बाद वो दिखा नहीं. That is the distance traveled, and from the trigonometry you can calculate the position of the electron. अगर वो एक पार्ट उसका ऑब्जर्व हो गया और एक पार्ट रिफ्लेक्ट होकर आपको दिखा, तब भी इंसिडेंट और रिफ्लेक्शन रिफ्लेक्टेड बोथ लाइट को देख के आप उसका पोजीशन मेजर कर सकते हैं. बट व्हाट हैपेंस व्हेन द इलेक्ट्रॉन ऑब्जर्व ए पार्ट और द total of the energy of the electron incident upon that electron, its velocity will change. Its velocity will change. So if you measure the position of the electron with the accuracy, then its momentum cannot be measured with accuracy. Okay. And if you measure the momentum of that electron accurately, that means it neither absorb any energy, it will just reflect back. then you cannot make the measure the position of that electron. Okay. So since due to the experimental reasons only, you cannot measure the position and momentum accurately with precision at a time. Similarly, you cannot measure the time and energy with equal precision at a time. So this is all about the Heisenberg uncertainty principle. You cannot measure the value of two canonical variables with accuracy. So energy time uncertainty principle, your position momentum uncertainty principle. The del x del p is greater or equal to h cross by 2. Del y del py is greater or equal to h cross by 2. Del z del pz is greater or equal to h cross by 2. So the uncertainty principle is a statement of the limit of accuracy with which a component of momentum of a particle and the corresponding position coordinate of particle can be simultaneously measured. For measurement, you need a light, maybe in visible range, or in X-ray range, or in microwave range, or in ultraviolet range. So when you measure it, if you measure the momentum accurately, then its position is not accurate. If you measure the position accurately, then there is error in measurement of momentum. And the product of del x del p is greater or equal to a constant, that is h cross by 2. Which we will also discuss in detail later on. The product of the probable errors in the measurement of the location and momentum of a particle is invariably as large as Planck's constant. Del P, del Q is greater or equal to h by 4 pi. So del P is probable error of measurement of momentum, and del Q is probable error of measurement in location or position. Similarly, you can have del E dot del T is greater or equal to h by 4 pi. H by 2 pi is equal to h cross. So you can write h cross by 2 also. So your position momentum are canonical conjugate variables. Energy time are canonically conjugate variables. Similarly, if you take angular momentum also, you can have an uncertainty relation. This is time energy uncertainty relation. And these are some experiments from where you can measure experimentally what we have discussed here. Then complementarity. It was proposed by Niels Bohr. The position and momentum measurement are really complementary and they are mutually exclusive processes. So there are consequences of uncertainty principle, the path of an object, 0-point energy, which we'll discuss during the discussion of your harmonic oscillator problem in quantum mechanics. The size of an atom, existence of electron inside the nucleus, angular momentum of an object, so on and so forth. This we will also discuss in detail later on, and also this Max-Born interpretation of wave function. So next is our mathematical treatment, which is very much used in quantum mechanics and which is the starting point of quantum mechanics. In classical mechanics, you have a Newton's law. F is equal to m d square x by dt square, or F is equal to ma, mass times acceleration. And your laws of motion, v is equal to u plus at, s is equal to t plus half at t square. So similarly, laws of motion and Newton's law is the starting point of your classical mechanics, and you can have kinetics and dynamics of objects in classical mechanics using these formulas. Similarly, quantum mechanics starts with Schrodinger's equation. So Erwin Schrödinger is a German physicist. Schrödinger equation. So Schrodinger's equation में you have a wave function written as psi. Psi. And the expression, there are differential equations as there is f is equal to m d square x by d square s by dt square or d square s by dt square. Similarly, here is also differential equation. Some are different. And in your classical mechanics, the Newtonian force law is having real part only, but here we have both real and imaginary parts. So let us discuss all these. I think it is visible now. So Schrodinger equation, it may be time dependent Schrodinger equation and time independent Schrodinger equation. So time dependent Schrodinger equation, let us discuss this first. And the simplest case is one dimension. Suppose a particle is moving in x direction. So this is one dimensional Schrodinger equation. So consider a non-relativistic free particle for simplicity, whose the velocity of the particle is very, very smaller than that of the velocity of light in vacuum. So it is a free particle devoid with any potential or force field, let us assume, and the energy is entirely kinetic. And if the energy is entirely kinetic, you can write E is equal to px square by twice m, where px is momentum and mass is represented by m, mass of the particle is m. So px is linear momentum, and your in de Broglie formulation, the free particle is associated with a plane wave of the form a e to the power I kx multiplied by x minus omega t, and which can be also written as a e to the power I by h cross px multiplied by x minus capital E multiplied by small t. So I is root over -1, which is a complex quantity. A is the amplitude of the wave. Kx is x component of propagation vector. K. P is h cross k, which is linear momentum, where h cross is h by 2 pi. And h is Planck's constant, and its value is nearly 6.626 into 10 to the minus 34 meter square kg by c. And x is your position coordinate of particle at time t, and omega is angular frequency. Are you getting it?
Yes, sir.
So this is your expression for energy, which is h cross omega, which is nothing but px square by twice. So this plane wave cannot represent a localized particle. We will discuss in later on what is localized particle, what is group, what is wave packet, what is group velocity, what is phase velocity in detail. A localized particle in X space is represented by a wave packet constructed by superposing a large number of plane waves, which will represent a particle. Wave packet can represent a particle. Wave has both real and imaginary part, and it never represents a particle. So you can construct a wave packet by superposing infinite number of or a definite number of plane wave number of waves psi. So psi can be written as integration from minus infinite to infinite a, which is a function of px e to the power I by h cross px multiplied by x minus e multiplied by t dpx, integrated over dpx. So now for simplicity, you can write A, which is a function of Px, is equal to 2 pi h cross to the power half phi, which is a function of Px. So now psi can be written as 1 by 2 pi h cross to the power half integration minus infinite to infinite phi e to the power I by h cross Px multiplied by x minus e t dpx. And your phi is regarded as the amplitude of a component wave of momentum Px, and it is independent of time t. So now obtain a differential equation that will satisfy regardless of the value of phi. Now differentiate psi. So del psi by del t, if you evaluate, you will have 2 pi h cross to the power minus half integration minus infinite to infinite dpx minus I e h cross phi e to the power I by h cross ex multiplied by x minus e. Okay. And your del psi by del t is equal to 2 pi h cross to the power minus half. You simplify it, minus infinite to infinite dpx e phi, which is a function of px e to the power I by h cross ex multiplied by x minus et. This is differentiation with respect to t. Then differentiate it with respect to x twice. Your del square psi by del x square is equal to 2 pi h cross to the power minus half integration minus infinite to infinite dpx minus px square by h cross square phi e to the power I by h cross dx minus et. So your minus h cross square by twice m del square psi by del x square is equal to 2 pi h cross to the power minus half integration from minus infinite to infinite dpx e phi e to the power I by h cross exx minus et. You can see minus h cross square by twice m del square psi by del x square. This value is equal to this value del psi by del t. You can see both values are same. You can see this value, the right hand side is same as the right hand side of this. So from this you can write I h cross del psi by del t is equal to minus h cross by twice m del square psi by del x square, where psi is a function of x and t. Now this is time dependent Schrodinger equation for free particle. Free particle matlab there is no potential in that point where the particle exists, and it is in one dimensional configuration in x space. And you can write it also in a potential, in the presence of a potential. Before that, let us have some operators which is very much useful for matrix mechanism later on. Let us have the operator formalism of this equation. So you can write this equation, Schrodinger equation, as shown in the screen as IH cross del by del t psi is equal to 1 by 2 pi h cross by I del by del x multiplied by h cross by I del by del x psi minus h cross square by twice m del square by del x square. You can write it as h cross by I del by del x multiplied by h cross by I del by del x. Okay, I multiplied by I square जब आपका क्या होगा -1, so -1 वाला हो गया, then h cross square your so IH cross del by del t. Am I audible? IH
Yes,
cross
sir.
del by del t can be represented as E cap. H cross by I del by del x can be represented as PX cap, where E cap is energy operator and PX cap is momentum operator, which I have also discussed during your mathematical physics class. Okay, eigenvalue, eigenvector, Are you getting it? Eigenvalue, eigenvector कैसे निकाला जाता था? Eigenfunction, when eigenfunction is operated when by some operator, you can have the eigenvalue multiplied by that eigenfunction. Energy operator E cap, when operated upon a function psi, it will give energy eigenvalue E. Similarly, momentum operator Px cap, when operated upon a wave function psi, it will give position, say momentum eigenvalue of that particle. So this equation can be obtained from classical energy momentum relation. In classical mechanics, you have E is equal to px square by twice m. You can see here px square by twice m. E cap psi is equal to px square by twice m psi. So here energy in classical mechanics P square by twice m. Here E cap is equal to px cap square by twice m. So this can be replaced by operators. While acting on the configuration space where there is only position vectors x, y, z, r, or only position vectors. This is in configuration space. So in configuration space, wave function psi px cap behaves as differential operator x cross by I del by del x, and E cap behaves as a differential operator I x cross del by del. So this is Schrodinger equation for free particle. Similarly, you can have Schrodinger equation in a force in a potential where there is a force acted upon each particle. So if you include the effect of external force that may act on the particle, then you can assume the expression for Fx is equal to minus del u by del x. This is a classical mechanical expression where u is the potential energy. So F can be written as minus del u by del x in one dimension, where u is a function of s, t, suppose. Then the total energy of the particle can be written as E is equal to px square by twice m plus u. So similarly, your Schrodinger equation will be modified as I h cross del psi by del t is equal to minus h cross square by twice m del square psi by del x square plus u multiplied by psi. And you know your I h cross del psi by del t can be written as h cap psi, where psi is a function of x comma t, x and t, where h cap is equal to minus h cross square by twice m del square by del x square plus u, where u is a function of x and t. So here your kinetic part is minus h cross square by twice m del square by del x square, and the potential part is u. And kinetic and potential, when you add or summation of these two, you have the Hamiltonian operator h cap. So your h cap is equal to h cap psi is equal to E cap psi. E cap psi is equal to h cap psi. Okay. So this is Schrodinger equation in a force and in a potential, and Schrodinger equation in the absence of potential or for a free particle. Similarly, time-dependent Schrodinger equation in 3 dimensions. This is in 1 dimension. If we extend this, the equation will be modified. In 3 dimensions, your x is replaced by r vector, position vector, where r is ix cap plus xi cap plus yj cap plus z k cap. And your a e to the power I k dot r vector minus omega t, it can be written as a e to the power I by h cross p dot r vector momentum dot product r vector minus et. So you can write psi as superposition of a large number of waves, psi or wave packet. Psi is equal to integration a e to the power I by h cross p dot r minus et pq p. And you can write AP is equal to 2 pi h cross to the power minus 3 by 2. In 1 dimension, it was minus half. In 3 dimension, it was minus 3 by 2 pi. So now you can write the Schrodinger equation as del psi by del t is equal to 2 pi h cross to the power minus 3 by 2 integration from minus infinite to infinite minus I by h cross e phi e to the power I by h cross p dot r minus et dqp. Okay. So in one dimension, you have written del square psi by del x square. In 3 dimension, it is represented by divergence, del operator. So del square psi is equal to 2 pi h cross minus 3 by 2 integration dqp phi e to the power minus I by h cross et I h cross del dot p vector e to the power I by h cross momentum vector dot product position vector p dot I. Now del p e to the power I by h cross p dot r can be written as e to the power I by h cross p dot r del p plus p dot del e to the power I by h cross p dot r. And you know del p is equal to 0 since p is independent of r. So you can write del dot p e to the power I by h cross p dot r is equal to p vector I by h cross p vector multiplied by e to the power I by h cross p dot r is equal to I by h cross p square e to the power I by h cross p dot r. Now the equation is modified as del square psi is equal to 2 pi h cross to the power minus 3 by 2 integration dqp minus p vector square by h cross square phi e to the power I by h cross p dot r minus et. Now you can see here your minus h cross square by twice m del square psi is equal to 2 pi h cross minus 3 by 2 integration dqp e phi e to the power I by h cross p dot r minus et. Is it visible in the screen? See. So your del psi by del t expression in the right hand side in the screen. I think the screen is, yes, it is visible now. So del psi by del t here in the right hand side and your minus h cross square by twice m del square psi in here at the right hand side, both the terms in the right hand side are same. So you can write I h cross del by del t psi is equal to minus h cross square by twice m del square psi, where psi is a function of r and t. And this is time dependent Schrodinger equation for a free particle moving in three-dimensional configuration space. It can be rewritten in the form I h cross del by del t psi is equal to 1 by twice m h cross by I del multiplied by h cross by I del psi, or your E cap psi is equal to p square by twice m psi, where psi is a function of r and t. Okay. So if you include the force in this expression, F can be written in a three-dimensional case minus del E. So use the potential energy. So the expression will be modified as I h cross del by del t psi is equal to minus h cross square by twice m del square plus u square plus u cap, which is a function of r and t psi, which is a function of r and t. So I h cross del by del t can be written as h cap e cap, and minus h cross square by twice m del square plus u cap can be written as h cap, Hamiltonian operator. So you can write E cap psi is equal to h cap psi, where h cap is equal to minus h cross square by twice m del square plus u cap, that is Hamiltonian operator. So this is three-dimensional Schrodinger equation, and it is a single partial differential equation. It is first order in time derivative. Thus, the time evolution of psi bears more resemblance to the diffusion or heat conduction equation than the propagation of elastic waves. It is a linear equation as it does not contain higher powers of psi or its derivative. Then dynamical evolution of quantum state. The time evolution of a quantum state represented by a wave function psi is described by the time-dependent Schrodinger wave equation. The wave function of a quantum state depends on position
and contains all information. This state wave function obeys the time-dependent Schrodinger equation. Knowing the initial conditions and the boundary condition, the state wave function of the quantum system can be determined through the time-dependent Schrodinger equation at any arbitrary time. Then the dynamic evolution of quantum state can be studied. Then the properties of wave function. So a wave function is a parameter varying with both position and time. It is a x dependency or r dependency and t dependency, and describes the wave associated with material particle as proposed by de Broglie. The wave function expresses the probabilities distribution of a particle in space and time, just as electromagnetic wave describes the distribution of electric and magnetic fields in space and time. According to de Broglie, a moving particle is associated with a wave known as matter wave. Hence, a wave function mathematically describes the wave characteristics of a particle and the probability distribution of a particle at a given point in space and time. The wave function is represented by symbol psi. Therefore, the wave function is not an observable quantity. The wave function is also called a state function because it gives information about the state of a physical system in accordance with the rules of quantum mechanics. And the wave function can be defined as the solution of the Schrodinger differential equation and provide a complete quantum mechanical description of a particle. Then physical interpretation of wave function. As I have earlier told you, wave function represents no physical quantity. So what represents a physical quantity? Wave packet or probability is a real number. And Max Born interpreted physical significance of the wave function by comparing a beam of matter particles with a beam of photons. So consider a beam of light or photons having intensity capital. So let us interpret wave function in the light of Max Born's interpretation. So Max Born considered a beam of light or photons having intensity capital I incident normal on a screen. So if capital E is the electric field vector or electric field of a beam, then the intensity of the beam at a point can be represented as capital I, and which is nothing but C epsilon 0 E square, where C is the velocity of light and epsilon 0 is the permittivity of free space. So you can write intensity I is directly proportional to E square, as C and epsilon 0 are constants. From the particle point of view, the intensity of light beam of a given frequency is proportional to the number of photons, capital N, that is passed through a given area per unit. Hence, you can write I is directly proportional to capital N, number density. From the above definition of the intensity, we have N is equal to E square. So, the number of photons reaching the screen is proportional to the square of the electric field strength. This relation is valid only when a large number of photons are involved. If we are dealing with only one photon, then the above relationship N is directly proportional to E square can be interpreted in a slightly different way. All point, the square of electric field strength E square is measure of probability that a photon will be at that location. So at point where E square is large, there is a high probability of the presence of photon and vice versa. Similarly, for matter waves, if psi describes a collection of many electrons, then modulus of psi square at any point will be proportional to the number of electrons expected to be formed at that point. So if psi represents a single electron, say an atom, then psi square modulus represents the probability of finding the electron at a given position and time. So psi square is often referred as the probability density or probability distribution. Max Born interpretation of wave function can be summarized as the wave function psi for matter waves is analogous to the electric field E for electromagnetic waves. The wave function psi is called the probability amplitude and is a complex quantity. Therefore, it is not a measurable quantity. Whereas the product psi dot psi star is equal to modulus of psi square is the probability density and expresses the probability of finding the particle at a given position and time. It is always real and positive number and hence is an observable quantity. The greater the value of psi square, the higher is the probability of finding the particle at a given position and time. The probability that a particle may be found in the region between x and x plus dx at a time t is t dx is equal to psi star psi dx or psi square dx, where psi square is equal to psi star psi or p is the probability density. The wave function used here is a normalized wave function. Normalized wave function and the volume integral psi square over all space is unity. So you can write E is equal to integration from minus infinite to infinite psi square dx which is equal to 1. When it is normalized, probability is 1. When it is not normalized, probability is not 1. When it is normalized, probability of finding the particle at that region is 100%. If the if it is not 1 or it is not normalized, then there is a limited probability of finding that particle in that region. Then probability and probability current densities in 3 dimensions. So rho dqr is the probability of finding the particle at a time t at the location r in the volume element dqr. The total probability of finding the particle somewhere in space is 1 or 100%. If the probability is 1 or it is normalized. For 1 dimension probability of finding the particle between points x1 and x2 is equal to the sum of probabilities rho dx in infinitesimal interval between x1 and x2. So it is thus represented by rho t x1 comma x2 and t is equal to integration x1 to x2 rho dx is equal to integration x2 to x1 to x2 modulus of psi square dx. So the probabilistic interpretation of psi can be well appreciated if and only if the probability is a conserved quantity. That is, if the probability of finding a particle in some bounded region of space decreases in time, then the probability of finding it outside that region must increase by the same amount. So in the universe, probability of finding a particle is 1. In a region, if its probability of finding that particle decreases, then outside that region, it will increase. So it is nothing but conservation laws. So we expect a related quantity called probability current density, which is analogous to the current density in electrodynamics to explain it. Suppose psi is represented one particle system. The probability of finding the particle in a finite volume omega bounded by a surface area A is rho is equal to integration over omega your psi star psi dqr. So probability flow across the surface A is determined by the time rate of change of probability. dp by dt is equal to integration over rho omega del by del t your psi star psi dqr. So this can be written as psi star del psi by del t plus psi del psi star by del t integration dqr. So from Schrodinger equation, you can have your del psi by del t and del psi star by del t as shown in the screen, having a minus sign only in the latter case. So your del p by del t is equal to integration over the omega psi star 1 by I h cross minus x cross square by twice m del square psi plus u psi plus psi minus 1 by I h cross minus x cross square by twice m del square psi star. Your u psi. So dp by dt is equal to I h cross by twice m integration over omega psi star del square psi minus psi del square psi star plus psi star psi your u psi minus psi u psi star dqr. So you assume u is real, so your psi star u psi is equal to minus psi u psi star. So psi star u psi minus psi u psi star is equal to 0. So you can write dp by dt is equal to I h cross by twice m integration over omega psi star del square psi minus psi del square psi star dqr. So if you have two scalars f and g, then it obeys the relation del f del g minus g del f is equal to f del square g minus g del square f. So f is equal to psi star and g is equal to psi. So you can write del psi star del psi minus psi del psi star is equal to psi star del square psi minus psi del square psi star. So by substituting these, you have dp by dt is equal to minus integration over omega del j dqr, where j is x cross by 2mi psi star del psi minus psi del psi star. And probability of finding the particle in a finite volume omega p is equal to integration over omega rho dqr is equal to integration psi star psi dqr. So this equation dp by dt is equal to integration omega del rho by del t dqr. You can combine this and you have integration over omega del p by del t plus del j dqr is equal to 0, where omega over which we integrate is arbitrary. So we can hold good if and only if the integrand vanishes, that is del rho by del t del j is equal to 0, or del p by del t del plus del j is equal to 0. And this is the equation of continuity. This is the equation of continuity. This is your equation of continuity. And this equation is encountered in electrodynamics as well as hydrodynamics. In electrodynamics, your rho is and j are represented by charge density and current density. Here it is probability and probability current density, probability density. And the rho represents the probability density here. So we therefore recognize j as probability current density. What is the expression for probability current density? We will discuss. So dp by dt is equal to minus integration a j dot n cap dA, where n cap is unit vector along the direction of d. And this is the equation of continuity. And you can see here the probability current density j can be represented as real part of x cross by mi psi star del psi, or x cross by m imaginary part of psi star del psi. Then if it is not normalized, you can normalize it. We shall discuss it in the next class. Am I audible?
Yes, sir.
Yes, sir.
I think there is some fluctuation both in the screen and in the voice. Or not?
Yes, sir.
Is there? Because here is heavy rain. There is heavy rain, and in this region, rain means there is no connectivity and nothing else. So let us have this class tomorrow. Tomorrow you have no class. So I think in this at any time the network can be disconnected completely. So I think if you will agree, then we can have this class tomorrow at 6:30 when there you have no class. Are you agree with me, or we shall continue this class?
Sir, I agree.
क्योंकि अभी नेटवर्क नहीं है, देयर इज ह्यूज रेन, ये कभी भी डिस्कनेक्ट हो सकता है, और बीच बीच में स्क्रीन भी मैं देख रहा था डिसअपियर हो जा रहा था. ठीक है. So expect a better weather tomorrow, and we'll have a further discussion tomorrow at 6:30. Okay, thank you.
Sir,
Thank you, sir.
Thank you very much.